Greetings, physicists. This video will be about how to solve problems that involve projectile motion. So let's get right into it. We've got a person in a kayak going over a waterfall, and what we're looking at is a position, not even a position versus time, this is a two-dimensional position or motion diagram for the kayak. So we're seeing the change in y as well as the change in x position. And these are 1 second intervals, so like that would be 0.1 seconds there, this would be 0.3 seconds here, this is 0.5 seconds there, 0.7, 0.9 seconds, like that. So there's something like 10 or 11 points there, that they're spaced 0.1 apart. Okay, and it says estimate the kayaker's velocity during the time interval from 0.5 to 0.6. And velocity here is, we could make it negative, I suppose. Let's look. So we're looking at these two dots, the 0.5 dot and the 0.6 dot. So let's get down to it. Obviously, the path the guy takes is this kind of curved path, but that's not really going to help us. We're gonna estimate. So by estimating, we're just gonna pretend that between 0.5 and 0.6 is more or less uniform motion, even though we know he's accelerating during that point. So graphically speaking, it looks like 0.5 is right at about 8.5 high, and 0.6 is right at about 8. So it looks like he falls half a meter. So I would say that's the delta y. And then if we look at the distance here from 0.5 to 0.6, it looks like 2.5 to 3. So it looks like it's also about half a meter. Delta x would be 0.5 meters. And the time interval there is 0.5 seconds to 0.6 seconds. So we have a delta time of 0.1 seconds. How do we deal with this? Well, let's do it with a triangle. Oops. Sorry, keep that there. Let's go here. I'm going to draw this that he goes y in this direction. He goes down half a meter, and then he goes to the right half a meter. So his actual distance traveled could be approximated by this vector, which would be half a meter, I believe, times the square root of 2. And then we can take that and say that the average velocity, now we know it's changing, but we're estimating here, so the average velocity between those 2 points was the delta x over the delta t, which is 0.5 times the square root of 2 meters divided by 0.1 seconds. And we can clean that up. I mean, if you want to divide 0.5 by 0.1, it's the same as multiplying top and bottom by 10, so 5 over 1 is just 5. And we would get 5 root 2 as our answer, so let's put that in the old calculator here. 5 square root of 2, and I get a little over 7, like 7.1. Hey there. 7.1 meters per second. So that's our estimation, and that happened because any projectile motion has some change in y and some change in x. Okay? That happens simultaneously. So let's go on to, let's go on to the next one here. The sport of dock jumping. This sounds an awful lot like a British sport. We're going to make the dog run off the edge of a dock and try and see how far. It's kind of like a long jump event, only you're doing it in water instead of in sand, and you're doing it with dogs instead of people. And the winner is obviously the one who jumps the farthest. I say obviously as if dock jumping was just this straightforward sport that we were all familiar with. Anyway, we're going to claim that this particular dog can run 8.5 meters per second, and he goes straight off. He doesn't jump up or anything. He just runs off the edge, and that the edge of the dock is 0.61 meters higher than the water, which is probably about 2 feet. So let's draw this. Here's the dock, here's the water, and here's our dog. There he goes, off the edge. And we're going to label some things here from this narrative. We know the dock is 0.61 meters, 0.61 above the water. That's a delta x. We know the dog was running at 8.5 meters per second straight. So his velocity, naught, is 8.5 meters per second. How far will he go? So the question is really asking for a distance, but it's asking for a horizontal distance. It's asking for this delta x. Whenever I do projectile problems like this one, which is most projectile problems, I like to separate my givens into columns so that I know which ones are in the y direction and which ones are in the x direction. So this v naught was in the horizontal direction. That's an x given. So that's a v naught equals 8.5 meters per second. I know that this is a vertical height. This is a delta x in the y direction equal to 0.61 meters. That's all they gave me. But you always got to be careful because in most projectile problems there are a lot more givens that you can suss out, that you can figure even besides the ones that they told you directly. For instance, the fact that the dog went straight off the edge means that he was not going up or down when he left the edge of the dock. So his vertical velocity, his up and down velocity naught, is 0. He does not start with a vertical velocity. He only starts with a horizontal velocity. If he had leapt at an angle, we could then talk about component vectors, but he didn't. We can also talk about gravity. Gravity acts only in the vertical direction. That's g. So the acceleration here, a in the vertical direction, is free fall. It's 9.8 meters per second squared. Now I'm going to make sure that I do something here, or I'm going to make sure that I say what I'm doing here. I have started this 0.61. I've started it measuring here and going downwards. So that's a downward 0.61, and I'm measuring my g downwards as well. So those can have the same sign. I'm making down the positive direction. You can do it either way. I'm just doing that because I noticed that the dog doesn't go up at all. There are no givens going up, so it just makes sense for me to do down the positive direction. But you can do it down the vertical or up the positive direction as well. Totally okay. So that gives me these 3 variables in the y direction. My x direction is kind of lonely. There's one more thing I can say about the x direction, and this is almost always true for projectile problems. This dog is not accelerating in the x direction. There's nothing pushing him forward, and not after he leaves the dock anyway. Once he's in the air, he's free falling. And in free falling, the only acceleration you get is straight down. Okay. Now let's look at our unknown. My unknown is this delta x, which is this delta x. So I'll mark that there. This is plenty of givens. I can solve with what I need. Now, unfortunately, the x direction here only has 2 givens, and for any of my constant acceleration equations, I need 3. The one thing that will help you is that in the x or the y direction, time fits both places. If you've gone for 3 seconds of time, you've done that in both directions. A time interval of 3 seconds is the same in the x and y direction. So what I'm going to do then is I'm going to solve for how much time it takes the dog to hit the water. And if I know that, then I also know how much time it took the dog horizontally. If that makes sense to everybody. So let's do it. Well, I've got x, v naught, a, and t. I think this equation will be useful to me. Delta x equals v naught delta t plus 1/2 a delta t squared. I will be solving for time. Now, normally this is a quadratic equation, except that my v naught is 0, so I can really just get rid of v naught, that entire term. And so I can then multiply by 2 and divide by a, and I will get 2 delta x, excuse me, that comes later, 2 delta x over a, and then if I square root that, I will get delta t, which is what I'm looking for. And I have all of those things. So, plugging that all in, square root of 2 times delta x, which in this case was 0.61 meters over, this was gravity, or 9.8 meters per second squared. And my meters will cancel. I'm going to have seconds squared left over. When I root that, I'll get seconds. Now I just need to plug in the 2 times the 0.61, divide by the 9.8, and get my square root. My calculator is telling me 0.35. So it takes about 1/3 of a second for this dog to hit the water. Now I got to figure how far he went. So I'm going to go back up here and say that my delta time is also on this side equal to 0.35 seconds. And look what I've got. V naught, a, delta time, and delta x. I can use the exact same equation. So the delta x in the horizontal direction will be v naught delta time plus 1/2 a delta time squared. But this time in the horizontal direction, when I plug in a is 0. So that entire term goes away. And I don't have to solve for delta x, it's already been solved for. It's already isolated. So I'm just going to plug in my v naught, which the dog jumped at 8.5 forward meters per second, times, we just learned that it was 0.35 seconds. Seconds will cancel. I'll get meters, which is what I'm looking for. So I need 8.5 times 35, which my calculator is telling me is just right at about 3 meters per second. If I round it, it's 3 meters per second. I said meters per second, but that's not the unit because the seconds canceled. It's 3 meters. So this dog jumped 3 meters forward. And hopefully that's a winning dock jump. Okay. Let's go on to our next one here. Soccer. Who doesn't love soccer? In a soccer free kick, this is, let's see, kicking a ball towards the goal. Goal is apparently 18 meters away when you do a free kick. And this particular player chooses an angle of 22 degrees. And he's going to kick with a speed of 23 meters per second. And we're curious about a couple of things. How long or how much time does the ball take to reach the goal? And how far off the ground will it be when it reaches the goal? There's some practical soccer math for you. So let's draw this. We got the goal over here, right? On the ground. And the free kick. That free kick, I'm going to label it with their givens. So we have 23 meters per second is the speed that it is launched at, right? And then 22 degrees is the angle. So theta is 22 degrees. That's right there. And it's 18 meters away from the goal, which looks like a horizontal distance. So that's a delta x is 18 meters. And we're looking for a couple of things. It's going to do one of these projectile bits. We're looking for a time interval. How long does that take? And we want to know, assuming it's not already on the ground by the time it gets there, we want to know that vertical delta x. How high off the ground is it when it hits? So just like I did before, I'm going to go ahead and separate all my givens into 2 columns. And I highly recommend you do this too. X direction, Y direction. So, in the x direction, we have the distance. We have a delta x equal to 18 meters. Oh boy. Well, now look at this. So this 22 degrees, this is interesting. This is both. This is a 23 meters per second. That's, oh gosh, come on. Draw better. 23 meters per second is neither in the x direction or the y direction. It's got components in both. So I'm going to have to make that a triangle. It's going to have some forward and some upward velocity. And I'll make that the angle theta, which we know is 22. Well, this means the horizontal is the cosine because it's adjacent to that angle. So this is 23 cosine 22 meters per second. And upward is the sine because it's opposite, so that would be 23 sine 22 meters per second. I'm just going to plug those right in over here. We've got the vertical velocity naught, this is the starting velocity, is 23 sine 22 meters per second. And I'm going to need more room here. Let's spread this out. Sine and then cosine for this one. V naught 23 cosine 22 meters per second. Okay. Now you should always be able to do acceleration. They will probably never give you acceleration for a projectile problem because it's intuitive. It's free fall. So in the y direction we have gravity. So the acceleration is 9.8. And in the horizontal direction, we don't have gravity. We have nothing. We have the acceleration horizontal is 0. So those two givens are almost always going to be the same thing. The exceptions to this are if they tell you that there's like a motor on it, like an airplane has a motor. And so it doesn't fall through the air, it flies through the air, and so there's a sideways push. Although in that sense you could argue that it's not a projectile, so... but that sort of information has to be given to you. It will not be intuitive. And this is enough. I can solve this. So my first question was delta time. Delta time, I have 3 givens on the delta x side. That is enough to get my delta time. So let's go ahead and solve for delta time. And in this case, I will use my delta x, v naught delta t plus 1/2 a delta t squared. And a is 0, right, in the horizontal direction, which is the one I'm doing. So I'm not going to have that term. So this becomes fairly easy. This becomes, and if I solve for delta t, I'm going to get delta t equal to delta x over v naught, which is equal to 18 meters over 23 cosine 22 meters per second. Let's put that into the old calculator. 18 divided by 23 cosine 22. And I am getting not even a whole second. Oh boy. So meters will cancel. I will be left with seconds. 1 over seconds, which is the same as seconds. 0.84 of them. Not bad. So my delta time is 0.84 seconds. Oops, I bled over into the y column, but it doesn't matter because remember time goes on both sides. So time is now also a given in the vertical direction, which will help because it was asking me how far off the ground is it when it reaches the goal. Well, that time interval was from where I kicked it to here. It's going to be the same time interval when I try to solve for the vertical distance because the ball's in the same spot there. All right, so oops, stop moving yourself around. There we go. So now I'm going to plug that 0.84 seconds into these givens, the vertical givens. So, I just noticed I have a problem. Vertically, the ball left the ground going up, right? So I made this value positive. But then I have to make gravity negative. because gravity is not going up, it's going down. So I have now values that are at odds with each other. Now I could make up negative and make gravity positive. That also works, but just don't make them the same sign. That will mess you up. So let's put this stuff in. It's the sign. So I'm going to use the same equation, delta x, v naught delta t, plus 1/2 a delta t squared. And I'm solving for delta x, so I don't have to rearrange anything, and I can just plug stuff in. The initial velocity was 23 sine 22 meters per second, times the delta time, which we just figured out is 0.84 seconds, plus, let me slide over here, 1/2 of a, which I'm making negative because it's downward, meters per second squared. So much space I need. And I have to multiply by the time, which we found was 0.84 seconds, and I have to square that. Okay. So this should be everything I need. Let's see what the calculator says. I have 23 sine 22 times 0.84 plus half of negative 9.8 and 0.84 squared. 0.84 squared. And my calculator spits out 3.78. Now let's see what that's going to be. Seconds will cancel here, and I'll be left with meters. Seconds squared will cancel with seconds squared, and I'll be left with meters, so this is all in meters. So it will be 3.78 meters off the ground when it reaches the goal. I'm going to look up really quick because I don't know that if soccer goals are that tall. A classroom ceiling is only 3 meters tall. How tall is a soccer goal? 8 feet or 2.44 meters. So this free kick, if I did my math correct, which I may have, this free kick looks like it completely misses the goal. This is going to go over the top of the goal. So that's a shame. All right, let's do our last one. Conceptual one. Love these. Baseball now, not soccer. Baseball player batting practice. He's going to hit 2 pitches. And look, I think that picture is the 2 pitches. So one of them he pops up, the other one he hits further out. But he hits them at the same speed. That's the important thing there. So let's mark that. Oops, let's mark that. Speed is exactly the same. So V naught is the same. Which ball is in the air for a longer time? Ignore air resistance. Good question. Well, let's apply some logic here. The vertical and the horizontal components of an object's motion do not interfere with each other. That's always true of any two-dimensional motion. So I could hit this thing really, really fast to the side, and it would not make it last longer in the air. But if I hit it really, really high up or fast to the vertical, it will stay longer in the air because that's really what's going to affect things here. So take note, if you were to take, let's say you have a gun. This is a tangent here, but trust me, it's relevant. If you had a gun and like an orange, let's put the orange here, and you fire a bullet from the gun and you drop the orange at the exact same time, and the bullet is going horizontally to start with, they will hit the ground at exactly the same time, even though the orange has no sideways motion and the bullet has a lot of sideways motion. They will both fall at the same rate. we need to assume, of course, that there's no wind resistance or effects from rifling and things like that, because a spinning bullet actually has some aerodynamics to it that are going to not make it follow that rule. But if this was like a musket and the ball just flew out straight without spinning, this would be true. They would fall and hit the ground at the exact same time. So all I care about is the vertical component. And in this case, both the bullet and the orange had no vertical component. So when I look at 1 and 2, I have to ask myself, who has more vertical velocity when they start? Well, 1 is at a steeper angle, and 2 is at a shallower angle. But they have the same speed. They have the same v0. So 1 will have this component upwards, 2 will have that component upwards, and 1 will have this component upwards. And we can clearly see that because 1 is a steeper angle, it should have a higher upward velocity to start with, so it should stay in the air longer. Because, and I think we can bring this around to an equation, the time that you stay in the air, well, let's see. Yeah, let's for a given. I'm about to second guess myself here. I think you can do it with this equation. Let's test it. A equals delta V over delta T. And for an object that you launch, right, it's going to go up, it's going to peak, and it's going to come back down. So we can say that V is going to be equal to the negative of v0. One will be going up and one will be going down, but they will have the same magnitude, right? And the acceleration is the same for both. So the time, if we solve for time, delta time will be equal to delta V, or V minus v0, over A. A is the same for both. V minus v0, well, V is equal to negative v0. So we can replace this, if I keep going here, delta time equal to V minus negative V over A, or equal to 2 times, well, I should do it the other way. I should replace it with v0 since that's our thing. With negative v0 minus v0, which is equal to negative, come on, it's not my day, negative 2 v0 over A. So the longer the time, obviously this is negative, but if you choose your axis to be the opposite direction, this would be positive instead. So the magnitude, though, the absolute value of this, the number of seconds it would take, is just 2 times the initial upward velocity for the object. So because ball 1 had initial upward velocity that was bigger, and I've dragged it out of proportion, there it is, it's clearly going to have more time. All right. Hopefully this helps you understand projectile problems and solve them in the future.